It looks like we're ready to start. So welcome, welcome everybody to our winter public lecture of the UCLA Space Institute. My name is Miguel Garcia Garibay. I'm the Dean of the Division of Physical Sciences, Professor of Chemistry and Biochemistry, and someone who's extremely excited about the Space Institute, and like many of you, and an entire aficionado of everything that goes above us, from the layers of the atmosphere that define the ionosphere to the planetary system and what goes on beyond, right? Stellar systems, black holes, the edges of the universe. The amazing thing is that UCLA covers all of that, right? In our faculty, in our various departments, in physical sciences, the School of Engineering, now increasingly more in the School of Medicine, people who are interested in space exploration, space science, space technology. We've seen the emergence of commercial space exploration over the last several years, and we've seen the resurgence, the renaissance of space in many different ways. UCLA is ideally positioned to really be a pioneer in space science exploration, technology, defining or helping define the future. There is a strong interest with our colleagues in the Anderson School of Management. So this is just one of the most exciting initiatives that goes on in our campus, and certainly in the Division of Physical Sciences. My colleagues in the departments of Earth, Planetary, and Space Sciences, Atmospheric and Oceanic Sciences, Physics and Astronomy are among the key players that, in fact, as you look at the history of space exploration, it is said, I've heard others say, and I think I've said Jacob Berning to say that UCLA has had an instrument on a role on every NASA space mission since the beginning of the the U.S. space program. Not only that, that UCLA had a presence already in the faculty in terms of space science, even before, the Sputnik era. So this is a remarkable place. And so we invite remarkable scientists to tell us about the excitement that is going on space exploration. And so today we have a very special guest here that will tell us about understanding the new Jupiter. But I will not make that introduction. I will let my colleague, Jacob Berning, do the honors. Please, Jacob.
Okay, thank you very much, Miguel, and welcome everybody. It's fantastic to see you all here. Welcome to the UCLA Space Institute Winter Quarter Seminar. It gives me great pleasure to introduce today's seminar speaker, Dr. Scott Bolton. Dr. Bolton is, of course, the principal investigator of the Juno mission, as you can see here, which launched in 2011 and entered Jupiter's orbit in 2016, making discoveries that have since rewritten textbooks about the gas giant planets. Prior to the Juno mission, Dr. Bolton served on both the Galileo and Cassini missions and focused on modeling the radiation environments of Jupiter and Saturn, the atmospheric and core structures of those planets, and the formation and evolution of the solar system in general. In addition to his work as a scientist, Dr. Bolton very interestingly collaborates with many artists to bring visual and musical interpretations of the outer solar system to a wide audience. He has consulted and appeared in numerous documentaries and strives to bring STEM outreach to students around the world. He's been widely recognized with many awards and recognitions, including several from NASA, JPL, AIAA, Space Pioneer Award for Science and Engineering in 2020, the Smithsonian American Ingenuity Award in 2018, and many, many others. So without further ado, let me hand you over to Dr. Scott Bolton.
Okay, thank you for having me. It's really a pleasure to be here back at UCLA. I used to visit here sort of early in my career when I was a student, and there was a professor in the math and atmospheric sciences named Professor Richard Thorne, I think he's passed away, unfortunately. And I remember one time I was trying to figure out some paper and I couldn't understand how the equations worked. And I asked one of the co-authors and they couldn't help me. And they said, call up Richard. And I called up this professor that I didn't even know. And I said, can you explain this paper? And the paper was from the 60s. And this was, I was 20, 30 years later. And he said, I don't remember the paper. What's the equation? Read them. And I read off the equation. I said, how'd you get from this step to this step? And right over the phone, immediately, he just said, oh, you have to assume this, do this, and then you evolves to that, and the equation goes to this. And I was like, wow, amazing. We stayed really good friends. And in fact, I, used to come visit UCLA all the time to see him. Okay, so what I'm here today to do is to talk about the mission Juno, which was, as they said, launched in 2011. It was a New Frontiers mission that that NASA selected, and it basically went into polar orbit around Jupiter. And I'm going to tell you about some of the amazing results. One of the unique things about Juno, besides the fact that it went into a polar orbit, is it got very, very close to Jupiter. And so you got really up close and personal to this giant planet. And what we learned is when we had many spacecraft that visited Jupiter before, Galileo and Voyager and Pioneer, and we more or less thought, scientists thought they understood pretty well how it worked. But when we got up really close and personal to it with Juno, we were surprised by a lot of things. And so I hope today that I'll be able to convey some of those surprises and why they're important and help you understand, how sort of there's a new Jupiter. And the first step of this is by just looking at that picture. Okay, so from polar orbit, you have a different perspective than we can from the Earth and all the other spacecraft. We're used to seeing Jupiter and it has these stripes, right? The zones and belts, and they're famous. And then you have the giant Great Red Spot, which is this very old storm that's been there at least since the time that we first had a telescope that could see it. So it's hundreds of years old at least. And it sits in the southern hemisphere. So this view of Jupiter was very foreign to us, right? And however, all of our children and their children's textbooks will have pictures like this in it, as well as the one that we're used to, because this is how Jupiter really looks. And you're looking sort of at the polar region, the northern pole, and the Great Red Spot from this perspective looks like it's up at the top, but it's really on the south. And you see that there's a fading of the zones and belts, and you see almost a bluish hue in it, and in the northern polar region, and those are all real. The colors are stretched like most of our space imagery. We stretch them to see the details. But the reason I want to convey this is that a lot of times in science, perspective is everything. And if you can gain a new perspective on a problem, and it's true of almost all fields of science, you will learn something new because you see it from a different angle, something different than you're used to. And so that's one of the key reasons that we have a space exploration program, is to go out and see these new perspectives, go out and visit them close up. And this is an example where you can see it firsthand, that you see a very different object. Okay, so right away, I'm having problems where the slides don't go forward. Hold on a minute. Try this. Okay. So the science objectives of Juno had to do with the origin of Jupiter, the interior structure, the atmosphere, and the magnetosphere, which I unfortunately covered with that last slide. Sorry. And so what you see is a couple of images. At the top is a model of an early solar system. If you're looking down from the top of a solar system, you see this bright spot, the proto-star, early sun. Does this have a pointer on it? I don't need it. I mean, but I don't want to push the wrong button. Well, that's a top button. It'll you can use the mouse. Okay. Whoops. That's forward. That's forward. Okay, well, you're finding out now that that it's a miracle that Juno worked. And so yeah, I'm not on that slide, but I'm gonna try to find the slide that I was originally wanted to be on. That's my whole talk. You saw it now. No. So I'm not great with computers or hardware in general. And all the time we were building Juno, my whole team was saying, please stay away from the hardware. And you just saw an experience of why that is. So this, I'm going to stay away from the pointer, and I'm just going to use this, which I think you can see. So this figure kind of shows this early sun, and then you're looking down and you're seeing the leftovers of what is a protoplanetary nebula, and then an artist's conception of what the first planet, which presumably was Jupiter, is forming out of that protoplanetary nebula. So the protoplanetary nebula is the leftovers after the sun forms. So we kind of think, scientists think that, stars form from clouds of material, nebulas, and they collapse on themselves and they point, and a star is born, and then there's leftovers in a disk that are left out. And it's got gas and dust, and rocks start to form, ices start to form. And from that, the planets must come. And Jupiter's thought to be important for understanding the origin because it's the most massive and the largest of all the planets in our solar system. And it is likely formed first because had it formed after the solar system was formed, it probably would have disrupted the orbits of the other planets. So it took the bulk of the leftovers. It's more massive than all the other planets put together. And so it took the bulk of the leftovers, and it's a lot like the sun. It's mostly hydrogen and helium. And then our other science has to do with understanding the interior. So we have two big questions that we want to understand for the origin, which has to do with, does Jupiter have a compact core? So did it start with a core of heavy elements in the middle, and then eventually get enough gravity that it brought in the gas and dust that was left over? Or did it form more like the star, where it just collapsed onto itself and maybe there is no core? So we set out to distinguish between those two ideas. And then also, what is the global water abundance? I'll get back to that, but that has to do with how much water or oxygen is actually in Jupiter, which really tells us a lot about the early solar system. And I'll talk a little bit more about that in a minute. And I think the other key piece to what Juno was doing was we were learning about Jupiter in part because it was our example of a giant planet, and we're seeing exoplanets now. We're able to see those with our big telescopes, and we're starting to see that there are giant planets out there, and they're very important in exoplanetary systems. We see things that sometimes don't make so much sense right away. We saw these giant hot Jupiters really close to their parent star where we didn't think they could form. We're starting to understand how solar systems evolve. And so Jupiter really helps us anchor that, because that's our example. So astrophysicists everywhere will learn about how exoplanets work by learning more about our own solar system. And it's not just Jupiter, but you'd like to know about Saturn, Uranus, Neptune, and of course, all the planets. But we also study the atmosphere. How do these work? What's actually below the beautiful cloud tops that we see in Jupiter? So Juno was set out to look at that, and also what's driving the aurora. So the bottom picture is a picture from Hubble telescope, and it's of Jupiter's aurora. Jupiter has aurora like the Earth does, aurora borealis, the northern lights. And that's a picture of Hubble looking at the ultraviolet emission, and you're looking at the pole sort of in the middle, and then you have this oval around it. Our Earth's aurora are a little bit similar. What's kind of unique about Jupiter's aurora is you can also see footprints of some of its giant moons. So it has 4 big moons called the Galilean moons, and you can actually see the footprints almost like there are particles passing from that moon into the atmosphere and lighting up aurora. And so you can see something called the Io footprint. Io is the moon of Jupiter that's very volcanic, in fact, the most volcanic body in the solar system. And you also see Ganymede and Europa, 2 other satellites that are of particular interest right now to people as we study habitability around the solar system. Ganymede is a large moon of Jupiter, and Europa has a liquid ocean underneath its ice shell. And I can see some of my colleagues, when I was young, I joined a team called Galileo, and some of my colleagues right here, Margie Kivelson's in the audience. Hi, Margie. She was actually one of the ones that discovered that ocean in Europa. And so it was a very exciting time. So you can see the aurora. And so what Juno is doing is really studying all of it, the magnetosphere, the atmosphere, the interior, and also trying to understand the origin and evolution. But before I go too much into Juno, I want to just say also something about the early solar system. So a long time ago, we thought we were the center of the universe, and that the everything was sort of zodiacal or mythology based, and you had the different signs all around the sky. And of course, this picture shows the sun in the center, but we used to think it was the earth in the center and everything went around us, right? And Galileo kind of changed that. So during the Italian Renaissance, there he was. He had a telescope. He had one of the first big telescopes, and he was looking at the skies from Venice, Italy. And so you see some of these early pictures. And he actually worked from one of the towers that were right on St. Mark's Square. And he looked up and he pointed his new telescope up at Jupiter, among other targets. And he drew this thing that you see on the right-hand side, where you see the Jupiter in the middle and a couple of bright things that were, in theory, stars. And as he looked in the different days, there were different stars that seemed to move around back and forth, back and forth. And keep in mind that people at the time thought we were the middle, and everything went around us. And he looked at these drawing that you're looking at and came to the realization that these were satellites going around Jupiter. And that was a pretty big leap, and it changed our perspective forever, right? He got into some trouble with the church for saying this, but we weren't the center, that there was another object out there that had things going around it. And it was basically his imagination and inspiration from looking at this. And he must have been a very brilliant guy to connect that. I'm not sure I would have been able to do it. But the reason it's connected to Juno is I want to show a movie that we made. So on the way in, we took a picture every 15 minutes as we approached Jupiter. And we had a very special camera, so other spacecraft haven't been able to do that. But we took a picture every 15 minutes, and we watched Jupiter and the moons, the Galilean moons, going around. So for the first time, humans were able to see motion in the celestial sphere and celestial bodies. And so what you're going to watch is what Galileo must have imagined in his mind. And it starts off with a little animation that is, you're sitting in Galileo's telescope, but once it clicks, it'll all be real. There's music to go with this, but I don't hear it. I muted it. It really needs the music. Are you sure? It's muted. That's not. We tested this, but this is just another example. Really sorry. The way to fix the audio. Maybe I might just start. You would be very sorry if that happened. I'm sharing sound from my computer. Well, you can see those going around anyway. And what you see is Europa, Io is the closest. Europa, they go around at different speeds. And you can even see Callisto is kind of blinking on and off. It's got very, not much, it doesn't reflect light as well. But it also is very weak, so it goes on and off. It's barely at the reflection level of our camera. But when you see them go behind Jupiter, they actually go into shadow. Like that. And so this is really what, not only what Jupiter looks like, but it must be what our solar system looks like. Far away. It's all the planets going around. I haven't heard movies that didn't have the music. Have another record. Oh, it's super instant. I didn't test it with Zoom. Campaign to quit Zoom because I think the music is pretty important, but okay, I'll go on because there's for another few slides, there's no music anyway. So so we're really trying to get at the history of the solar system. And so we know Jupiter is like the sun because it's almost all hydrogen and helium, which is what the sun, and in fact, that's what most of ordinary matter is that we know of in the universe. But we also know that it's enriched in heavy elements. So with the Galileo mission, we sent a probe into Jupiter and we learned that the heavy element enrichment was real, and heavy elements to a cosmologist is everything heavier than helium. But we really want to understand how Jupiter formed that could get more of these things called heavy elements than the sun. We don't have a good understanding of how to do that. And so one of the tasks for Jupiter was for Juno was to understand that a little bit better by looking at, in particular, water. And I'll show why that is important in a minute. But what I want to point out is that what cosmologists call heavy elements are very important to us in our understanding where we came from, because these heavy elements, these elements heavier than helium, are really what we're made out of, right? It's what life comes from. And so we're really looking at our own history. And so what we're after is, what's the recipe to make a solar system? So if you really wanted to understand a recipe, let's say you tried that soup and you liked it and you said, okay, I'm going to try to make this at home. So what would be the first thing you might try if you didn't know and you didn't have a phone that you could Google chicken soup on and look it up? So you wanted to find out how to make that. You'd turn that can around and there would be an ingredient list. And that would be a good start, although my guess is that ingredient list would have a whole bunch of things on there that you can't pronounce that are preservatives, and you wouldn't really get a clue. But the basics would be, you'd see chicken and some kind of noodle and some vegetables and water, and you'd start to get an idea what the soup was made out of. And so we're sort of like that when we're trying to understand our solar system recipe. We're at that ingredient list stage where we're going back to all these different planets and trying to understand the ingredients and how they're different wherever we go visit in the solar system, and try to put together from that what the recipe was like to make a solar system. We have some more advantages lately because we're able to look at exoplanetary systems, and that's also showing us how planets are made. So here's the sort of a table of the elements from high school that you may recognize. And of course, hydrogen and helium are the top two. And so to a cosmologist, is apart from hydrogen at the top right and or top left and helium on the top right, all the rest of them are heavy elements. And you can see lots of them that you might recognize. C for carbon is number 6, and 7 is nitrogen, 8 is oxygen. You got a lot of stuff that's the basis of the organics and things that we think are important to habitability. You got a couple other ones that might be your favorites. You could look up, Ag, or PV, or, gold or silver might be something that you're fond of. But anyway, we're really looking at the things. And on the left side, on the right side, you have the red ones, which are noble gases. And so those are important for us to measure because they don't change a lot in chemistry. And so if we can understand those, so when Galileo probe went in to Jupiter, and here's a picture of it falling in, this was back in 1995. And this is actually what the Galileo probe looked like. It was like something right out of a science fiction movie. And it was a probe. It was basically a submarine for Jupiter, and it had a bunch of instruments that stuck out, and it went in with a parachute and a heat shield, and it measured the composition of Jupiter is one of the key things that it did. And what it came back with after about 20 minutes or so, it went down and it measured argon, krypton. You see on the bottom of this scale, the x-axis, so to speak, the horizontal scale is argon, krypton, xenon. Those are the three of the noble gases. And then you have carbon, nitrogen, sulfur, and oxygen. And these are all tied up. The carbon, nitrogen, sulfur are tied up into molecules. The oxygen is in water. The nitrogen's in ammonia, but it doesn't matter. We're trying to measure how this compares to the sun. So on the vertical axis is the ratio to the sun's composition as best we know it. This is kind of an old figure. It keeps getting modified as we learn more about the sun's composition. But what you see is that most of the elements are all enriched by about a factor of 3 or 4, except for water or oxygen, which is depleted. It's the only one that's depleted. And we believe that scientists that first saw that and didn't understand it, and they thought that it meant that we may have gone into the Sahara Desert of Jupiter, so to speak, and just got unlucky because it was supposed to be well mixed. And if you had a lot of water, you might say that they provided the ices that went into Jupiter that basically explains the enrichment. And so getting that water abundance was really important in understanding how Jupiter formed. And it was a real puzzle when it came out depleted, because almost all scientists believe that Jupiter was enriched by ices that went in. And so how could it get all enriched and have the ice be depleted? Or the water be depleted. So this was a big puzzle. It was one of the challenges for Juno. And so we built Juno and designed it to get that data along with the core data and study the magnetosphere and the atmosphere. So here's a picture of Juno. It's a solar powered spacecraft. It's very large because of Jupiter's far from the sun. So each of those solar panels are 8.5 meters long a piece. And they only produce about the power of a microwave oven, even with all of that, because it is very far away. And you can see the different instruments. We have about 10 instruments on there. At the end of one of those solar arrays is a magnetometer boom that's very stable, and there's a magnetometer on there plus 4 cameras to locate it in case it bends. That's going to study the magnetic field very precisely. JADE and JEDI are charged particle instruments that look at the aurora. SRU is a camera. It's called Stellar Reference Unit. It's actually an engineering camera, but we use it for science. Its specialty is low light. It's looking at stars for navigation. So when we navigate with spacecraft, it's kind of interesting that it's not a lot different than the way we navigated with ships, right? They would look up at the stars, see where they were, and figure out where they are. And if you knew where all the stars were, you'd know kind of where you were. And we do the same thing with the spacecraft. However, because it's able to take pictures of starlight, it can see things very low light. So we also look at the moons and atmosphere of Jupiter in special ways to see that. Gravity science is really looking at what's called a Doppler shift. So the spacecraft goes by, that's an antenna that communicates with the Earth. And as the spacecraft goes by Jupiter really fast, it's getting really close to Jupiter. The Jupiter's gravity field kind of pulls and pushes and tugs on it and changes the trajectory a little bit. And that change shows up in a frequency shift in the communication signal. So we call it the Doppler shift, which is a relativistic term. But what happens is that blue light or red light can shift. If it's things moving away from you, the light will look a little redder. If it's moving toward you, it'll look a little bluer. That's true. That's sort of high frequency versus low frequency. And so when we look at the Doppler shift, you can actually hear this if you're just standing really close to a train or a bus. When it goes by really fast, you'll hear it go, right? It's changed frequencies as it goes by. It's sort of the same idea. So then we have some remote sensing. We have a JunoCam, which is our camera visible light. It's a color camera. Ultraviolet, UVS is an ultraviolet camera and spectrograph. Jurum is an infrared camera and a spectrometer. And then WAVES looks at plasma waves. So it's a very, complete package of science on Juno. And this goes through space spinning. So this whole contraption spins twice per minute. And all the instruments are designed to look out in between the solar arrays, more or less. And so everything gets a chance to look out, and we're spinning twice per minute. So this is a very large spacecraft that would barely fit into this room, right, in one direction, and it's spinning twice per minute. So it's quite large. So one of the first things that we did was we have a giant program for citizen scientists or amateurs, in that we take all of our data and we put it on to a website, and anybody, including all of you in the audience and anybody listening, can go make their own pictures of Jupiter or anything that Juno has taken an image of. We put up the raw data, you can play with it, you can learn how to process it, you can change other people's images. And so we have citizens and scientists all over as amateurs watching Jupiter. And there was a guy in Clyde, his name was Clyde, and he lived in South Africa, and he was an amateur astronomer, and he was looking up at Jupiter one day back on June 2nd of 2020. And he looked up and he was looking at the Great Red Spot, but he saw this big white spot, which you see. See if I can get my cursor to go there. This storm here, it's kind of a circular white storm, and it was new. So he contacted us and said, hey, I see a new white storm. And it just turned out to be lucky. A couple of days later, we were going over the exact spot. So we took this image. This was not his image. It'd be hard to get that image from Earth, but we went over in high resolution and took a picture of that white spot, and we named it Clyde Spot because he discovered it. And then one of the reasons I want to show this is that we're learning about atmospheric evolution. So we're all suffering. You guys are seeing it as much as anybody in California here with these, what they call atmospheric rivers that keep hitting, right? I happen to like to ski, but if it snows so much, the ski resorts actually close. So we don't understand weather that well on the Earth. We're trying to. But when we took a picture of this, about a year later, you can see how that white spot changed. And now it was a very turbulent, kind of topsy-turvy set of clouds that are intermingled, and it's become an entire different look. And that's showing us, we see a lot of those kinds of things all over Jupiter, but we didn't realize until we saw this, that you're actually watching a storm that starts out looking like it's cyclonic and very well organized as a circle, evolving into something that's quite a tangled mess. And so we're learning about that. And of course, we see some of that happen on the Earth as well when we see hurricanes and tornadoes. Another thing that we learned is when we went over the North Pole, we took a picture and there were giant polar cyclones surrounding the North Pole. We later found out that it was actually surrounding the South Pole as well. What's strange about these polar cyclones are configured in a geometric pattern where they're evenly distributed in angle. Almost there's 8 of these around, and they're located at like the points of an octagon. So they're evenly distributed, and they're pretty big. These are, the size of the United States or bigger. So these are not small little storms. And on the other pole, there's a very similar set of cyclones, except there's only 5, and they're distributed at like the points of a pentagon. And so this was a really big surprise. There's a center one. Now, we've been watching this for years now and monitoring the pattern of these. Scientists are still working out the details of how these storms form and how they're maintained. And they're making some good progress on it. But what's kind of interesting is that over time, we sometimes see one, it seems like a gap opens up and a new one is coming in. And you'll see pictures where there might be a 9th one that's going to form. And we think, okay, the next time we go around, we're going to see that. But in fact, by the time you come around, it's been booted out and they're back to the 8. And this has happened over and over again. And so I believe that this is a very exclusive club, and they don't just let anybody in. And they start to, but then they say, nope, you don't make it, and they kick them out. And it's kind of interesting because we don't have a good understanding of why that would be. But somehow there's a stability here. Now, this is a little different. You might have also seen Cassini, which was a great mission that orbited Saturn, got pictures of its poles. And we also saw what we call the hexagon there. And those were different than this. They were lines that were shaped like a real hexagon. It's like what seemed to be at the pole of Saturn. This is polar cyclones, right, that are just distributed like a polygon. So there's no lines going between these. So Jupiter's very different than Saturn. And we were really surprised when we first saw this picture. And this is an infrared picture. So what you're looking at is heat, and the white is warmer than the dark, and the red is in between. And generally, Jupiter is warmer as you go down. It's still cooling off from its formation. So as I go down into the atmosphere of Jupiter, it's getting warmer and warmer. And so when I see stuff here that's white, I'm probably looking deeper down into the atmosphere. And when I'm looking at the dark stuff, you're looking at the top part of the atmosphere. That's just sort of a very oversimplified way to interpret some of this data. But I'm going to stay on the atmosphere here. So you can see on the left here, you see how Juno kind of works. It's spinning. We have this one instrument that was invented, really. I invented this for Juno. It's called the microwave radiometer. And basically, it's like radar, but it's only listening. And what it's doing is it's measuring the temperature of the atmosphere. And there's 6 different frequencies. And each frequency measures the atmosphere at a different depth. So a very long frequency, long wavelength, low frequency, I should say, sees deeper because the atmosphere appears more transparent. And at a high frequency, the atmosphere is more opaque. And so I see higher up. And so it measures something between 1 bar of pressure all the way down to maybe it gets data that's even hundreds of bars pressure, maybe even 1,000 bars. 1 bar of pressure is the pressure of our atmosphere at sea level. So we're more or less near sea level here, right? You're a little bit higher than the ocean nearby. But so the pressure when you go outside is 1 bar. So as you, just like when you dive into a pool, you'll start to, or in the ocean, you feel your ears, you know, you go down a few bars or whatever, you start to feel it. Jupiter is of course a giant gas ball, and it seems like you're going down deep, hundreds of kilometers, maybe down deep. But when you look over to the right, you see that stripe of Jupiter where it's lit. You can see that we're hardly going in very deep, but we're seeing big changes in the atmosphere. And what we're there to do is to measure this temperature as a function of depth. And because of it's tied to opacity, we're basically measuring ammonia and water, because those are the things that are really responsible for Jupiter's opacity at these radio frequencies. So on the far right, you see sort of a little profile of what the atmosphere looked like. The thing on the very left on the outer edge is sort of the top part of the atmosphere, and then coming in deeper is this part right here. So that's the deep part of the atmosphere, and over here is the top part of the atmosphere. And what this is a map of ammonia, sort of similar to temperature. And red means there's a lot, blue means there's almost no ammonia, and yellow means it's really high amounts of ammonia. So the first thing we saw, which was a kind of a surprise, is we knew that ammonia was depleted in certain parts, but we didn't think it went down very deep in Jupiter. And so we saw that that blue region really went down really deep. And then we saw this thing that is almost like what I would call an atmospheric river, but it's along Jupiter's equator. It's full of ammonia. And there's a stripe around Jupiter's belly, right around the middle, that's very, very high in ammonia. And it stays high all the way down as far as we can see, with a little bit of a curve to it. The other thing that was funny is that it increased down at the very bottom. This is well below the condensation level of ammonia and water. And so the theory was that once you dropped into below the clouds where the condensation occurred, everything would be vapor, right? I'm going down and I go from ice to liquid to vapor. It should all just be mixed up once I get down there. And in fact, that was the basis of the Galileo probe data that I showed you earlier. And what we found was it wasn't mixed, and we didn't know why. And in fact, that was a huge surprise to us. And it was a bit of a shock to people that study the atmospheres of Jupiter. So I'm going to come back to that in a minute, but keep in mind that Jupiter is not well mixed, and there's some puzzles about how it works as you go down just in the first few hundred bars, first few hundred kilometers. So another thing that we did was we had that low light camera, and so it started taking pictures of Jupiter in Jupiter shine. So we would be on the night side. Or it wasn't Jupiter shine, it was one of the moons that were reflecting light back on, so you can see a little bit of the clouds. Here's one of these pictures from this Stellar Reference Unit camera. It just sees in black and white, and it took pictures of lightning flashes. So Jupiter's atmosphere was known to have lightning, and there's quite a bit of it, but we were studying it much closer than anybody could before. And what we discovered was that the lightning was smaller than anybody had ever seen before. So the lightning flash, the size of the lightning flash, is our way to determine how deep is the electrical storm that's causing the lightning. Where is that thunderstorm residing? And the reason is that once the light is emitted, just like on the Earth, it goes out in a spherical, it goes out in all directions, and it makes a pattern at the top of the atmosphere. And however big that is, you can then work it back and say, okay, then the lightning must have been this deep. This lightning was so small that it implied the lightning was coming from a depth where liquid water shouldn't exist. It was too cold. It should all be ice. And most theories of lightning have the common lightning, although you can make it in other ways. The most common kind of lightning is believed to need water or some kind of fluid in 3 phases in order to build up the charge. So I need ice, I need vapor, and I need liquid, all kind of around with near each other that you can build up these charges. And so this told us that there was a liquid way up where liquid water shouldn't exist. And so the idea is how do we solve that? How could that possibly be? And we developed up some models, and one of them is that the ammonia is penetrating the ice and it's almost acting like an antifreeze, right? So I end up with this ammonia water mixture, and its freezing point has changed, right? From just pure water. It's like Windex used to be like that. I think now they make it in a cheaper way that it's not just ammonia and water, but it used to be ammonia and water, like a cleaning fluid with water mixed. So here's a toy model, and we ended up developing something that hypothesized that hail or something like mush balls, we call them mush balls, but they're mushy hail, were forming in Jupiter up at the high levels. And I needed this ammonia water mixture to do this. And I could seed these hail things, and they would go up and down and build hail just like it does on the Earth. And then once they got heavy enough and big enough, they'd fall. And just like hail, if you're in a hailstorm, you'll see this hail come and land on your driveway or on the street. And it's a chunk of ice, and yet it can be way too warm, right, for ice to exist. But it's come down so fast that it didn't have a chance to evaporate or melt. And so that's a way to carry down what you would think are volatiles and end up with something that's not so well mixed. And so here you see on this side, on the left side, is actually a close-up of the data that we got from this microwave experiment on Juno that shows you that depletion in blue and the white, or in the yellow, I mean, enrichment of ammonia, and then all the variability that we see down very deep. And the left side is pressure. So 10 to the 0 is basically 1 bar. So that's like up at our sea level. And then you have 10 bars pressure. And then the next ones go all the way down to 100 bars. And you can see that we were seeing mixtures changing way below where we think the water cloud layer would be, which is way up at a few bars. And so we put together a toy model, and we attached thunderstorms in order to make the hail. And so the little blue squiggly line is sort of the number of storms that happen, an occurrence rate sort of a storms. And of course, there's very few storms around the equator, but they're more, we can see this because we can measure lightning. And so Juno looked at all the lightning, and we figured out where the storms were, and we put that into this toy model, and you reproduced almost pretty well the Juno data on the right-hand side. It almost matches this figure. It's not completely right, but it kind of led us to believe that this mush ball or hail is playing an important role. So while we were doing this, I'll just tell you kind of a funny story. So I was trying to figure this out. We were trying to figure out how to move things around using rain, but the rain couldn't get down deep enough to really change things without evaporating. And then I live in Texas, and there was a big hailstorm going on. And I thought, maybe we need to move solids. And I started to think about it, and I was curious. So I ran out in the middle of the hailstorm to go get some and start to play with the hail and see what it was made out of and how it works. And then a big hail piece came down and hit sort of a picnic table that I have in my backyard and just went right through it. And I looked at that and I thought, what am I doing out here? And I have no helmet. You need a helmet. And I ran back in the house. And when I told my team, they said, it's a good thing you didn't get hit. So I'll just tell you that being a scientist has its dangers. So anyway, so the importance of I just want to kind of go over a little bit of why the oxygen and carbon and other things are important in Jupiter. So the first surprise is we found the oxygen was varying at great depth, and we tried to figure out what that meant. And it might mean that something like hail or some other exotic process is going on in Jupiter. But at a very fundamental, it means that giant planet atmospheres work very different than our simple models. There's something complex going on. The second surprise we had was when we looked at the gravity field and we try to solve for it, we find that it suggests very low heavy element abundances. It doesn't have room to put oxygen and all of the heavy elements that we learned from Galileo exist in Jupiter. And so we're at a sort of a puzzle, because we have one set of data that says there's heavy elements in the atmosphere, and we have another set of data that says deep in the interior, they may not exist. And yet all of our theories have Jupiter was supposed to be well mixed. And so we're right away trying to understand, okay, what's the communication between the atmosphere and the interior, and can it really be different? If you have something heavier on top, it should go down. I mean, it's just like it works in everyday life, right? It should mix in. It's hard to keep them separate. So, so Juno's results kind of throw out a big caution to a lot of scientists that study giant planets, because maybe the atmosphere and the giant planet doesn't work the way we really think. Maybe Jupiter formed in a funny way, maybe it evolved in a strange way and the atmosphere works differently, but it also helps us understand exoplanets. So you have this incredible tool, James Webb Telescope now, that can look at exoplanets and see oxygen and carbon and starts to put things together. So there's many exoplanet astrophysicists that aren't completely aware of our results right on Jupiter, because it's in our solar system and they look at far away things. And so they assume everything's well mixed. So they're sitting there looking at the oxygen and carbon ratios, and they're trying to learn about, well, could this planet be habitable? How many organics could be on this? And what does it mean about how this planet formed? How can I link that back to its parent star? And what we're realizing because of Juno is that maybe that carbon to oxygen ratio at the top of the atmosphere is not telling you about the body as a whole. Maybe the interior is different than the atmosphere. And maybe what's happening is you're seeing things come in at different times and somehow they stay separated. So we have to be very careful. So when we look at the carbon and oxygen on Jupiter, we're really looking at weather, and the weather is complicated. And so that is going to inform people that are studying astrophysics. So there's a link between how we learn in our solar system to what we learn in other solar systems, and how we figure out whether we're really alone in the universe or not. Okay, so here I wanted to illustrate some ideas of what the core of Jupiter looked like. And one day somebody sent me a picture of a cake that they had made. And they were really proud of it, and it was pretty impressive. And then they cut it open, they actually had made layers that fit theories. Unfortunately, by the time they sent this to me, and I had to tell them that their model was wrong, that we had taken data and we now know that Jupiter doesn't look like that inside, although at the time we wrote the proposal, that's what we thought existed. So this is going to be another example that was a little bit like the atmosphere, in that here's the idea, is that does Jupiter have a dense rock core in the middle or none at all? And I kind of laid out why we want to learn that. And so here's a standard model on the left side where you have hydrogen at the top. It's a little bit depleted in helium, but then you get to this place where the pressure is so great that the hydrogen becomes metallic. In other words, it starts to be conductive like a metal. And then the question is there a dense rocky core? And I don't mean rocks like we have in our backyard. I mean heavy elements that are concentrated at the center, and everything's not well mixed. On the right-hand side is probably the best example of what works with our data. And that is that the core is actually not concentrated. There is a heavy element enrichment in the middle, but it must be diluted and fuzzy and go all the way out. So you can see at the bottom, instead of a small core, it's kind of big and loose and fuzzy boundaries. And we also have now learned that we believe there's gradients in this, and that as you go down into Jupiter, the amount of heavy elements versus the hydrogen is changing at different layers. And this is all brand new, although there are many models now being formed to do this. At the time we were writing the proposal, this idea was never really thought about much. And we actually wrote in our goal with NASA was the state of the science community's knowledge at the time, which was, does it have a compact core or none? And we were going to determine that. And what we found out was we weren't even asking the right question. Because neither of those cases was true. Instead, there's a giant fuzzy core. And so one idea of how to make that, although scientists haven't figured out how to make this work exactly, is maybe Jupiter was hit early on in its life, and it shook things up, and its core got distributed somehow. Although the initial models using that idea don't turn out to match our data either. It could be that we just have to keep working at it. That's one idea. There's other ideas that are being worked to try to solve this. but something strange went on with giant planets. And just to confuse things even more is Cassini at the end of its life and at the end of its mission went into an orbit that was a little bit like Juno in order to study the interior structure and the magnetic field really close up. And it found some of the same similarities. It's not exactly like Jupiter, but its core also may be gradients and dilute and sort of fuzzy. And so that may be, we're learning about giant planets a little bit with these two missions. So another thing that we had was the magnetic field. And so here's a movie of how complex this magnetic field. So you may remember when you were in school there, you would play with what was called iron filings and draw out a dipole, right? And that's a well-ordered magnetic field. It comes out the poles, it wraps around, comes in, looks a little bit like what this picture looks like. But when I spin around Jupiter and I want to see what this magnetic field really looks like, it's not very dipolar. You'll see that as we spin around, we see these other poles, multiple poles come up. The region in the red starts getting distributed, and then there's this big black or dark blue thing in the middle in the south, almost like a great red spot. In fact, our team called that the great blue spot. It's not exactly lined up with the great red spot, but it's similar. And then you can go over the poles and you can see it's not some little concentrated North Pole. And then you have this big pole like that's not at the pole at all, this blue thing, and then you have the bottom is a little bit different. So Jupiter's magnetic field is pretty complex, and this is helping us to understand how magnetic fields are created in the first place. And they're very important throughout astrophysics, but it's a very strange place. We've actually been able to see some of this magnetic field change over time since we've been there. So we've measured what we call secular variation. So far, only Earth has been able to measure that, but we now have seen it on the Earth, on Jupiter, so another planet. So it's really kind of exciting. Let me see if I can get, so here's another picture of that great blue spot. Once in a while, the great red spot must go under it. It's just a little bit south of it, or north of the great red spot. But what you have on that is I'm showing these black lines, that curvy line going across. Those are the actual zonal jets. That's the zones and belts of Jupiter that you're used to seeing, the stripes. And when it's way over to the right, it means the wind's blowing from the west to the east, very strong. And when there's a curve over to the other side, represents the wind or the moving from the east over to the west. So you have westerly and easterly winds. And what you can see is that although the blue is really circular, there's this stretched aqua color that's almost following the winds themselves. And so it gives you an idea that maybe the winds are distorting the magnetic field a little bit, although at some point the winds must stop because the magnetic field in Jupiter is just too strong to push around. But so we're searching for this magnetosphere or magnetic field atmosphere coupling that must be going on. And it also couples into the interior. So one of the amazing things about Juno is that we've kind of merged those fields. Magnetosphere and interior, magnetic field, gravity field, and atmosphere are all now intertwined physically. And until you really get up close to a body, you might not see that interaction. Here's just an infrared image of the aurora. I just want to take a quick picture as we looked over it. So I talked about the fact that Io has a footprint. And when we looked at that Io footprint, the Io is the volcanic moon, you see that it's actually not a spot at all like we thought it was. It's actually a whole bunch of wiggly lines. And so we're trying to understand the physics of really how that's made. And here you see a trail. Io spits out something, volcanic material all around, and it surrounds Jupiter in its orbit with these charged particles that we call the Io torus. And it also produces an auroral signature. And when we got really close up and saw high resolution, we saw that auroral signature was actually split. And so we're learning the physics of how that would work as well. So then we went into an extended mission, and we were lucky enough to be able to go by Ganymede. So here you see a picture of Ganymede, one of those moons that I showed in the very early part of the film. And although I'm now at a point where you should have music, but you won't, and I apologize for that. Maybe if I just unplug this part and just, well, maybe you can just listen to it. I can figure out how to get the movie started. Let's see, my speaker must be somewhere, right? Here, can you hear it now? So this is real images of Ganymede. And we're approaching on the dark side. So this gives you a little ride as if you were on Juno, looking down on your vacation. Music is by a composer that I work a lot with who passed away just last year, named Vangelis, who did Chariots of Fire. So we went by Ganymede, and then 6 hours later, we were going to fly by Jupiter. So you'll see that turn the spacecraft over to look at Jupiter. And now we're approaching Jupiter from its dark side over the pole. These are all real images. They haven't been touched up or anything. It's not science fiction. The only thing that's added is I took the liberty of adding lightning flashes based on where we see the lightning flashes, because the camera couldn't pick them up, but that didn't have the dynamic range. But we put them where we see them. They're around these white peripheral clouds that are very high up, that are tied to this ammonia ice, probably this water ammonia mixture. So where you see these lightning flashes and where these swirls are, you can imagine it's a hailstorm. And you can see that Jupiter is a very beautiful place with a lot of really swirling clouds. So you can remember the image I showed you of Clyde's spot, some of these twirling, intertwined, beautiful atmospheric structures kind of started off as simple hurricane and they evolved. And that's only about 5,000 kilometers above the cloud top. Right over Jupiter. We couldn't get any closer without fearing that we'd hit the atmosphere, and we couldn't go any further out because we thought we'd hit the radiation belt, so we were like threading the needle. And then you see this form of all those white storms that go along in a string. They call that the string of pearls. There's, you know, as you heard, I do a little bit with art and science, and I'm quite involved in that aspect of it, of the both art and music. And so I think I try to make these videos that kind of mix them all together. One other one I'll play. Let's see if I can get this to play. So this is plasma wave data, and the reason I wanted to show this is that this is data that is basically radio frequencies, or local, what they would call plasma waves, and they're turned into sound. And the person that kind of did that was a UCLA professor named Fred Scharf. That was the first time I had ever heard of it. He was working on Voyager back in the 70s, I guess. And this is an instrument similar to what he did there. And he turned it into sound and listened to it. And I used to do that a lot when I was working on Galileo. And basically it's sometimes at a frequency that the human ear couldn't hear. We hear about 20 to 20,000 hertz. And so all they've done is convert it with a mathematical routine into the hearing range. And then you play it. Now, if you were on the spacecraft, you wouldn't hear this, right? It's a vacuum out there. The sound needs air. But nevertheless, it's more like what's coming over your radio. And so the magnetosphere is making this sound. You're watching actually the charged particles around Ganymede, and where it goes up higher in frequency in the middle there is getting near Ganymede closest approach. So frequencies go up. Scientists use this to discover all kinds of things. As I remember back in the days of Galileo, us looking at this and what was going on both at the Earth and also Europa and Ganymede, and we would playing this. And so this was Juno's version of it. I have another more evil side of me that I use this for Halloween. And I would play these out of my speakers and kids would get scared. And I had a young daughter. She's now 18, but back when she was, 10 years old, she'd be not looking out the window and I would make the house very, very scary and play these sounds. And she'd say, there's another kid that got scared. They dropped their candy basket and ran. And she'd go out and get the candy basket, And so it became a theme of our house. So next, in last September of 2022, we went by Europa. So Ganymede was June of 2021. And you can see we captured this image of Europa. What was interesting is you looking along the terminator, you can really see the topology and so forth. I don't have a movie of this made yet, but here's an image. The highest resolution image we managed to get was of Europa with that SRU, that star camera. So here, this is looking at the night side of Europa lit by Jupiter shine. So remember I showed you a picture of Jupiter lit by a satellite, by Ganymede shine. This is the opposite. This is Jupiter lighting up Europa, and you see this strange feature. You see these roads almost going across, crisscrossing. These are cracks in the ice and all kinds of different kind of tectonic type things that are all over Europa. You're looking at an icy body. Both Ganymede and Europa are just giant ice shells. And the one behind it that looks kind of fuzzy, that was the best image we had before Junos. And so we just pasted this on top so you could see the difference in the resolution. And so we're sort of struggling to analyze this. The papers aren't out yet, but we're looking at that feature, and the dark parts might be deposits that are old or radiated, and things where liquid might have come to the surface, or vapor or some kind of a thing has changed. And it's really fascinating. And of course, there's two missions that are working now. One is JUICE, which is going to go to Ganymede, and it's going to launch later this year. And then Europa Clipper is another mission, and that's going to launch next year to study Europa. So these are sort of precursors, and we're learning about it. Another thing we do is we study Io from a distance. So these are infrared pictures of Io, the most volcanic body in the solar system. All these little yellow spots are volcanoes going off. And so some of them were taken from very far away. And so we barely can see, but you can see the whole place is like a pizza. I mean, it's really out of control. And, but as we got closer, the two bottom ones are taken where you're looking at about, 15, 16 kilometer resolution. It's some of the best stuff where we're monitoring and we're actually watching the volcanoes vary. So some of them are turning on and off and getting brighter or less. We're discovering new volcanoes. But also we're seeing a territory that hasn't been seen before. Some of these images are looking right at the North Pole, which we hadn't been able to see until we got above Jupiter's equatorial plane. And so Juno did that for the first time. So we're coming up, we're doing, these are PJ numbers. We're now on the 50th orbit. So on the 51st orbit, we'll be even closer. Then 53, we get even closer, these kilometers. These ones were taken at maybe 50,000 kilometers and 80,000 kilometers. So we're going to get really, really close. And then in December of this year and then February of next year, we'll fly by Io at a distance of only 1,500 kilometers. So we're going to get really close to this body, which is doesn't have a lot of spacecraft that have gone really close by. And then, and so I just wanted to show this because it's kind of an exciting, you're really watching how volcanoes go on and off, and there's never really been a study of that. Somehow, this little moon, it's spewing out volcanic material, and it's driving Jupiter's magnetosphere, which is gigantic and unbelievably powerful. And yet it's being driven by this little moon spewing out material. And Jupiter's magnetosphere is one of the largest objects, maybe the largest object in our solar system. It stretches all the way back out to Jupiter, to Saturn's orbit at times because of the solar wind. And so if you were to see Jupiter's magnetosphere, and you could see it with your eyes, from the Earth, it would look like it was almost the size of the moon. So it's quite big in the solar system. And then I show you just a picture of Io. So the next things I just want to say, what's really next? Well, what are the missions that are coming up? So I mentioned JUICE, which is a Ganymede orbiter that'll launch in I think April if it goes on time. And then Clipper, NASA has a mission called Europa Clipper that'll launch in 2024, and it's a Jupiter orbiter, but has a lot of Europa flybys. Whereas JUICE launches and goes around Jupiter for a while, but ends up orbiting Ganymede itself. And then there's an Ice Giant mission that's being studied now. Maybe it'll launch in the late 2030s, maybe even further out than that. And it'll study Uranus, but eventually we'll study Neptune as well. And Neptune has a moon that's might also be interesting to study called Triton. And then you have, of course, JWST and ALMA. ALMA is a telescope that is able to take this picture that's the background of this. This is an exoplanetary system, and it looks a lot like theorists thought solar systems form. You get this planetary disk that I talked about in the early part, the protoplanetary nebula, and you get these regions carved out where the new planets are formed, and they basically absorb all the gas and dust in their orbit. And so it kind of looks like a phonograph record, right? But it's actually really matched a lot of people's models, and it's really an important tool along with JWST to understand other planetary systems. And those are all important in understanding, are we alone? We're looking to see, are there other Earths? Are there other places where there might be life? And these are all part, and there's a couple of future telescopes, Roman and Plato, that'll come out that'll also be able to look at exoplanets in unique ways, and dark matter and dark energy as well. Okay, I just want to put a plug in because besides music and science and art, I'm really into education and STEM education in particular. And I had help starting a program back in the 80s at JPL called the Goldstone Apple Valley Radio Telescope Program. And it uses a NASA telescope that was donated to us when they were retired for kids, students between middle and high school, although we're getting into elementary schools as well. They actually can control that telescope that you see in that picture from the laptop in their schoolroom. And then they make an observation of Jupiter in the radio emission, and then they do science with us. And they do science. And so it's all over the country as well as now international. And it's a big program. And if UCLA has any kind of STEM education programs that touch on local schools, we'd certainly like to help out with this. This is a great program in order to get kids doing science, real science, and learning about it. And some of them have done so well that they've actually published papers with the Juno team. So that's quite impressive. So I'll end with just a few pretty pictures. Here's Juno's pictures of one of the campaigns where we studied the Great Red Spot. You can see right away that we're orbiting in a polar fashion because you're seeing that strange thing, but you can really see what it looks like close up. And here's one of those storms. You see these little white edges. You can actually see the clouds. Or I should say the shadows along some of these. So you can see that some of the clouds are higher up than others. And generally, when you're looking at these different colors and formations, you're looking at different depths. And so you can see it a little easier in this with these shadows. We're actually working right now to try to establish the altitude of these shadows so we can figure out how high and the different cloud decks are. And these are places where you see a lot of those thunderstorms. It's also quite pretty. Keep in mind that all of our data is pumped out to the public, and we do these things called citizen science where they make it so the names of some of the people that actually made the image are down below. They've also chosen the color schemes and to bring out different features. So Tanya's particularly a little bit more artsy than some. Dave is also pretty good at doing this. So we're seeing different people that work with us. Some of them are really extreme in the art side, which is all good. I tried to trigger the art thing a little bit early on in the mission. I put out some that were really exotic art pieces so that others would feel comfortable to do that. And we're now able to inspire a lot of artists to think outside the box. And some of them pointed out that Van Gogh already painted Jupiter a long time ago. And I have to admit that was a fair comparison. And I was a big Van Gogh fan. In fact, I used to teach French Impressionist in college, so it was kind of nice to see that. And so here's another one that's art. And then sometimes you just use your imagination, and you get away from the science all together. So here's a couple of people that mix together a science picture with an art picture, and then some little kids doing some almost like crayon-like work. And then finally, somebody who really imagined themselves going there. And so I think that was a good thing. And so I think that's the last slide.
Thank you very much, Scott. That was a fantastic presentation, and it's fascinating to see science as it is unfolding, kind of happening in real time. So we have a few minutes for our audience Q&A. We have a microphone up here at the front. So if you have a question, I would encourage you, if something interests you, come up to the front, use the microphone, please, and ask Scott anything you might be curious about.
Pass it around too.
How many more years do you know? Well, that's a good question. So I didn't mention much about the difficulties of Juno, but there's Jupiter is a monster. And it has radiation. It's basically a planet on steroids, right? Everything about it is extreme. So we're shielded like an armored tank. We haven't seen any hints that we're having problems from the radiation, except we're starting to see a little hiccup from some of the cameras and things, but everything's functioning at the moment. We're well into our extended mission, right? We finished our primary mission in 2021. So what NASA did was I didn't want to have to propose many extended mission things. And so I worked out a deal that we would propose one that would go as long as I thought we might last. And so they approved it through the end of 2025. But it's not showing any signs of a problem. And so my guess is that as we approach that in 2024, if everything's working well, we'll have to put together another extended mission proposal to be considered. At some point, if the radiation doesn't kill us, which someday it will, we'll run out of propellant. But we don't know when exactly that'll happen and if you run out of propellant, then you can't point the antenna at the Earth. You can still go around Jupiter, but you can't send your data back. So that's not very useful. So my guess is that we've got a couple more years, maybe 2 or 3 years, maybe a little bit longer. And then there'll be a long period where we'll get for data analysis and publications and things like that. But I think that if we are still getting data 3 years from now, that's probably a good guess.
Are there any more satellite flybys in the cards after Io this winter? Is it still possible to do more?
Well, there are no more Galilean satellites closer in. There are these really tiny satellites that are inside of Io's orbit that in theory we haven't looked to see if we can fly close by one of those yet, but they're pretty close in. And it's a pretty hazardous region. You're getting really into problems. So I don't think there'll be really close ones, although we're going to start going through the rings of Jupiter, which are close in. And that's going to be a very exciting time because they're not very well explored. We'll be one of the first spacecraft to really go into those and be able to make a lot of measurements on them. And one of the things you want to see is how the dust that's partially charged particles and dust are mixing together in this ring system. And there may be clumps of things. So some of our imagers might be able to pick up some of that.
Yeah, Scott, you mentioned rather quickly that Jupiter may or maybe is conclusively formed before the sun. Can you
No, I misunderstood. If I said that, I made a mistake.
Okay, so has Juno shed a little bit more light on who came first?
Well, I think there are no theories that suggest Jupiter came before the sun.
Okay.
If I said that, I said it wrong, or it was misunderstood. What I meant is Jupiter is likely to have formed first among the planets.
Okay.
So you still have to get the star, the sun, forming, and then we're forming from its leftovers. And that's the whole game, is to compare our Jupiter's composition with the sun's, because something changed. And I don't know of any theories that have been put together that suggest another planet forming before Jupiter. That would be hard to do because Jupiter's so massive. My guess is that things started to come together early in the solar system, what we would call planetesimals, and maybe there's different names now, pebbles, and they're all little rocky, icy things that are of different sizes. Some of them go in and build up comets or create asteroids. And so you might have primordial things being built there that are small. And then those things all go in and make a Jupiter and the other planets.
I had a question actually, since you mentioned the small particles. Have there been any observations of asteroid impacts from Juno? Like, have you seen anything streak through the atmosphere like that?
We have seen some things. We don't know. I don't know if we call them asteroids, but meteors, or bolides. We see some things, but most of them that we've seen we've seen some with this SRU camera where we saw things that we thought were lightning and then it had a streak. And so we thought, okay, that's not consistent. What else could that be? And then you see some things in the ultraviolet. So there's a couple of papers published mainly from the ultraviolet team talking about things that are happening high up in the atmosphere.
If I recall, you had to adjust the mission plan based on issues with the satellite. You had to slow the number of orbits for Jupiter compared to the original plan. Have you fully compensated for that change at this point?
What we did was we changed the orbit period. So we made it, so what really happened is we didn't change it. We were planning. Okay, so when we got into orbit around Jupiter, we were in an orbit that took 53 days to go around Jupiter. And then our plan was to go around a couple times and then fire the main engines and shrink the orbit down to 11 days instead of 53. And we started to get nervous about that. We first thought we might change it to 14, and so we were going to change it to that. But then as we approached the time to fire that engine, we were testing the rocket engine and saw that there were issues with it. It's got rocket fuel and an oxidizer and things in it, and it was pressuring up and it wasn't behaving exactly the way it was supposed to. And so we realized that if that mixture went wrong, you could lose everything. And we had a working spacecraft at Jupiter. So we decided that we could just stay at the 53-day orbit and not change it at all. And we would get essentially the same science, maybe even better. And it would take longer, right? Because it was 53 days for each orbit, and we're a mapping mission. So we have to go around 30 times, and 30 times 53 is a lot bigger than 30 times 15 or 11. And so we had to convince NASA that that was the right thing to do. They agreed after looking at it and said, okay, we'll let's leave it at that. And so there was no compensation. We just stayed at 53 days. We did have to do a couple of hiccups, like we stayed on there so long that we went into occultation behind Jupiter, behind the sun. And that scared me a bit. We're a solar powered spacecraft. You're supposed to stay in the sunlight. We only had batteries for so long, but the navigation people are like wizards. They figured out a way to hop over that shadow. So we hopped over it. And now in the extended mission, we go through many of these occultations or things into the dark side of Jupiter, but we're going to use them for science and get occultation measurements of the atmosphere. And they're all less than 2 hours, so our batteries cover it, no problem. So it turned out that that decision to stay at 53 days was, I thought we were going to try to make lemonade out of lemons, but I think we might have made lemon ice cream because that is what enabled us to go by the satellites. It's enabled all this other science, the secular variations that I mentioned, the fact that the magnetic field changes. I mean, just a ton of science came out of the fact that you just were able to study Jupiter longer. And I would like to say, I had the vision and knew I was doing this, but that isn't true. I mean, we fell into it. We figured out the best way to deal with it. And the only thing I can say is our team was clever enough to make use of the opportunities. And I'm happy that that was part of the plan.
I just wondered, what are the plans for disposing of the spacecraft at the end
I was
of the
waiting
mission?
for that question. Good one. So as you know, on Galileo, we had to dispose of Galileo. So we launched with a plan that in order to avoid crashing into Europa and possibly contaminating it, because we'd like to study that for habitability, we would dispose of it. So what Margie's referring to is you take the spacecraft due to something they call planetary protection. And because it has germs from Earth on it, you dump it into Jupiter and let it burn up rather than accidentally hit one of the satellites. And that was our plan. Then when we got our first extended mission, we said, okay, we're going to go buy the satellites. It's just naturally evolving and the orbit is twisting around. And once we were proposing to do the extended mission, it was going to start in July or August, I think August 1st. And by September 22nd or September of 2022, within a year of that, we were going to go buy Europa, and it was impossible for us to get back to Europa and accidentally crash into it because we don't have enough propellant or anything to move the spacecraft back. So we have proposed to NASA and the planetary science community, planetary protection community, that we can't get back to Europa by accident, and that you could just let us naturally evolve and we will eventually fall into Jupiter, but without pushing ourselves in. And that has gone through much of the approval, but it hasn't got the final stamp yet. But I believe that that's probably going to be the end result, because we've been able to show that we pretty much can't contaminate the satellites anymore. Another, blessing, accidental blessing. Question?
Okay, if there are no further questions, let me tell you about the plan. We were supposed to have a reception out on the patio, but believe it or not, a whole river flew in the air from the Pacific and changed our plans. We will still have a reception, but we've now moved it to the main dining room. So let's thank our speaker one more time and see you there.